Okay, so this will be worksheet number 12 from lecture number 12, and this will be your last worksheet. And lecture number 12, we talk about oscillations and waves. So we discuss about the waves under two categories, that we have longitudinal waves and you can have transverse waves. It doesn't matter which wave you have, but still there are some important properties of all kind of waves, right? So we discuss about the period, that will be the time to complete one cycle. If you measured in units of second, this will be the period. But if you measured it by using the meters, this will be the wavelength, right? And this height, we call it as amplitude of the wave, right? So all the wave have the velocity, we'll be able to calculate by using frequency and the wavelength, right? So in addition to that we went through the intensity, right? We talk about the intensity of the sounds, because we talked about the sound waves, right? We talked about the intensity of sounds, and then we discuss about how decibel will take and how it will convert into like intensity. What is the relation of the decibel to intensity relation? And we talk about the range that we can hear, threshold, intensity, and hearing damage, that how decibel will affect to the damage of our hearing, those kind of limitations. And then we move into the some important information about the spring oscillations. And the spring will oscillate when you have a mass in here. There is a period for that. And also we talk about the simple pendulum. If you do the back and forth motion, this has the period informations, right? So this has the period equal to 5 m over k square root. And this one has the period of T, simple pendulum, 2 pi, length divided by the G, right? Length is this length, right? And then we talk about simple harmonic motions. So simple harmonic motions can have very specific way of writing the formula. Simple harmonic motion should have oscillations that we can write the acceleration with the time equal angular frequency squared and displacement with the time. So this is the simple harmonic oscillations formula, right? So in addition to that, we went to the sound instruments, how frequency instruments, how frequency will change by changing your fingertips position in the sound instrument, and also string instruments will follow the same. How we create harmonics to make different frequencies, we discuss about that, right? And last, we discuss about the Doppler effect. So Doppler effect is basically happening in sound waves and also light waves that you're going to discuss in next class. But Doppler effect for sound waves we discuss in here. That means basically frequency shift. Due to relative motion. So we discussed that also. So now worksheet will be focusing to those concepts in more details. Okay, so now let's move into the first question. Explain longitudinal waves and transverse waves. So you can explain this yourself, because I explained those two different waves in the class. So longitudinal waves means basically you have like a spring, right? So, or else when I talk, I make a sound, then my sound waves will come to your computer, then you will hear it, right? That kind of oscillations that the particle in between my mouth and the computer going to vibrate. So those we call it as the longitudinal waves. So that means longitudinal waves basically have the motion like back and forth motions. You can have like a sprint kind of motion. Velocity of the wave is this way, but each individual particle will stretch or compress, then that will create the longitudinal waves. So important thing in here is we can say individual particle back and forth motion. Back and forth motion means you can say parallel or anti-parallel. Wave velocity. So those are, we call it as longitudinal. So this is the direction of the velocity. They will do back and forth motion because of the parallel or anti-parallel motion of individual particles. So example for that is, you can say, sound waves. Okay. And so now second one is transverse waves. Transverse waves will be like, you can actually draw it as a wave, right? What will happen is your wave is still moving in this direction. Velocity is still that direction, but your individual particles, you will see they are going up and they are going down. So that means in this case, individual particles are moving perpendicular to the waves. Wave velocity. So those we call it as the transverse waves. So now I can give the example for that. Light waves. Right? And so now let's move into the scene. Which of following acceleration you can identify as simple harmonic oscillations, and why? And what is the angular frequency if it is a simple harmonic motion? So now, as I mentioned in the theory part, also acceleration, we will be able to write negative omega squared and displacement time. So this is the format of the simple harmonic oscillation. Any simple harmonic motion, this should be the equation of simple harmonic motion, right? So now, according to the three things that I have it in here, so you see that the first one, negative is missing definitely, so that is not a simple harmonic motion. And second one, negative is missing, that is also not a simple harmonic motion. Third one, I have negative, so that is seems correct. And then omega squared, probably this value. And do I have X after that? Yes. So that means only possibility in these three, correct one is this one. So other two are incorrect, right? Now I'm asking why, because it follows the simple harmonic oscillations equations, right? And next, what is the angular frequency if it is simple harmonic motion? That you can see omega squared. If you compare this equation into this equation, you can write omega squared equal 4. So that means omega will be 2. And as I mentioned, omega will be the angular frequency that has the units radians per second. So that will be the frequency of the simple harmonic motion. Okay, so now part D and E is talking about the spring pendulum and the simple harmonic pendulum, simple pendulum. So now there are two pendula have different length. One has the length L and the other one has the length 4L. How do you compare these two periods? So now this one is simple pendulum because it's a length, right? So simple pendulum, as we know, you're doing the motion of the pendulum back and forth, and if it go here and come back here and go back here, this is what the period is, time for one cycle. So that period is depend on, as we discussed, 2π L over G. What that means is period is independent of the mass. It is only depend on the length and the gravitational acceleration. Other than that, there is no change, right? So now if I do it for these two cases, the first one I have this one, length L, but the second case I have length 2π 4 times L over G, right? So now if I rewrite this by taking 2π and L over G, keep that, but I have root 4 there, right? So that means I have 2π L over G root and 2. So what that means? So what that means is I have 2π L over G as T1, that exactly same as here. That means I will be able to write this as twice of T1. So now my final answer, period of the second pendulum is equal to 2 times of the period of first pendulum if you use the 4 times of the length core to do the oscillation. So now let's move into the spin pendulum in next question. So there are two spin pendulums. One has the spin constant K and the other one has the 2K, but you're going to attach into 3 kilograms mass. So you have a spin pendulum. The mass is still the same, but you have different K value. So now if you do the oscillation of this one, we know it is going up and down, right? So now period of spin pendulum will be equal to 2π M over K and root. So now let's do the same thing for the 1 and 2. 1 is this one, and 2, you do not change anything else. You're just going to change the spin constant into twice of the K. So now this will be equal to 2π. M over K is still there, but I have 1 over root 2 left, right? So now if I compare these two equations, this will be your T1. I'm going to replace that in here. That means this will be 1 over root 2 times T1. Okay. So that means I will be able to write T2 is equal to 1 over root 2 times T1. Okay, now part F is asking you to convert 180 decibel. Decibel is the unit that we measure the sound, right? So sound intensity. So now we can convert 180 decibel into intensity. Intensity we measured by using watts per meter squared, right? You remember that the sound intensity that we talked in the beginning, sound intensity in decibel is equal to 10 times log I over I naught. So I naught is the threshold intensity that is given, that will be 1.0 times 10 to the negative 12. It is a constant watts per meter squared. That also will be equal to 0 decibel if you think from the decibel. Okay, so now we need to convert into 180, right? That's right, 180 decibel is equal 10. This log is actually 10 base, right? And I divided by I naught is given 1.0, 10 to the negative 12. Okay. So now we need to find the I. So let's divide by 10 first in this side. 180 divided by 10 is equal, right? So I'm going to write it is 18, right? 18 equal. And then we have log base 10 I over, let's write 10 to the negative 12 in here, right? So now I need to calculate this. That means if I take the 10 to the power in both sides, what will happen is 10 to the power 18 here, and then 10 to the power, you have log 10 I over 10 negative 12, right? When you take the log 10 to the power, that means this and this cancel out basically. So that means you will left 10 to the power 18 equal I over 10 to the negative 12. Then you're going to calculate the I. 1.0 times 10 to the power 6 watts over meter square. That is equal to 180 decibel. Okay, and now I'm asking question, is that enough to damage your hearings? So yes, because hearings can your ears can be damaged within the range like 120 and more decibel. So damage greater than usually 120 decibel. Okay, since you have 180, definitely it will damage hearing, and from the intensity, this will be equal to 1 watts per meter square. That's the limit that you can hear without damaging the earrings. But even less than 120, probably less than 100 is not good. Okay. Okay, now let's move into the second question. In the second question, we are working with the frequency and harmonics, basically, how you hear the harmonics and what is the frequency that will create when you change your finger position of string instruments or sound instruments and those things. So now draw and find the frequency of first two harmonics for following tubes. So now first one is a tube open at both ends, right? So let's draw the diagram first. You have the both open end tube like this, right? So now as we discuss how the sound will travel in here will be, this is the first harmonic that you're going to hear. So this is, we call that the node, right? So now you need to understand, if this length is L, how you going to compare this into wavelength? So that's the important part that you should understand. Now wavelength is, if I draw the wavelength in my drawing, we know that wavelength will be one cycle. That means this kind of things, right? But what do you see on here? You will see you have opening here, and the node in the middle. That means the part I have inside the tube will be basically this part. You have the extra opening here, but this is the part that you're going to see in here. This is the part that I draw it on the top, right? But this is what the wavelength is, right? But this is what the length is. Now, how do you relate the wavelength into length is important. I hope everybody can see the length is half of the wavelength in here, right? So now when the length is half of the wavelength, we know that we can write the frequency equal velocity over wavelength. That means the frequency you're going to hear, velocity divided by wavelength, is 2 times L in here, right? So that means if I want to find the frequency, let's say this is F1, that's your first harmonic, will be velocity divided by twice of the length of the tube, right? Since it is asking first two harmonics, we're going to do the next one also. You do not change the length, but you're going to change the frequency to create a second harmonic. So now how do you create the second harmonic in here? What is the pattern that you're going to see? You still should have opening here, right? And also opening in here. And then you're going to draw your waves, going one and upcoming one. And then you will see, you're going to find it out what wavelength you have it in here, right? It is definitely more than the wavelength now, because you have basically two loops. You see that this is one loop, this is half a loop, this is half a loop. That means you basically have two loops. When you complete two loops in here, that's similar to the wavelength. That means in here, L will be exactly wavelength, right? So you can keep moving according to the other harmonic. So F2 will be velocity over wavelength in here is definitely L. So now frequency 2 will be velocity over length L. Okay, now let's move into the next one. So a tube open at one end. So you have one end open, you need to find the first two harmonics, right? So length L, length L. Let's do the first harmonic. So now when you have this end close, what happen is you have this wave and reflect back from there. That means your opening will be this end, but your node will be here. That is the first harmonic you can hear, right? So now according to your wavelength relation, check that this one will be basically half of the loop. You see that this part is not even complete the loop. It is the half of the loop, right? That means it will be 1/4 of the wavelength. Half of the loop means, you see that it is 1/4. This wavelength is divided into 4 pieces, basically. So that means L will be in here equal to 4, or 4L equal wavelength. That means frequency will be equal to V divided by 4L in here, right? It is the first one that you hear. And then the second one, what will happen is, again, you should have the same pattern, but you're going to do a one loop and the half, right? So one loop and the half. So that will be basically 3/4 wavelength, right? 3 lambda over 4. So that means the frequency will be velocity divided by wavelength. That means 4L over 3. So 4L and 3 will go to the numerator. So now this will be first harmonic. This will be next one. Okay, so now let's try to answer the question that I have with part E and C and D. Right. So C is asking, you blow into the open tube and produce the tone. What happened to the frequency? What happened to the frequency of the tone if you close end of the tube and blow it again? So, but you are using same length, two tubes. You can use the information, you have it in there. Also, I'm going to draw it in here. So you have two open end and you have one closed end. Both lengths are same length, right? So now in this one, first harmonic, as we discussed in the top, it will create like this, and this one create like this. And we talked about the frequency for this one. First one is V over twice of L. This one, first one was V over 4 times L, right? So now you can definitely see frequency is greater when you have both end open. Okay, so you will hear the lower frequency. So what happened to the frequency of the tone if you close one end? So that means, according to the question, answer is you hear lower frequency. Now let's try to do the next one. You have long pipe and the short pipe. Which one has the higher frequency? Now it doesn't matter. You use the close or open, both tubes will be the same. So let's use the both end open, but one has the short length and the other one has the longer length. Let's say this is L1, this is L2, and it will create still the same first harmonic, right? We know that the frequency will be V over 2L1 in here, and frequency here will be F1 will be V over 2L2. So what we know is L2 is greater than L1, then which one has higher frequency? Higher frequency will be whichever you have lower length. That means short pipe. So short pipe has higher frequency. Okay, so now last question about the Doppler effect. So now Doppler effect, as we discussed, it is a frequency shift that you will hear because of relative motion of the observer and the source, right? So now these questions, it is very important that you understand what is the source is, what is the observer is, and according to that, using the formula that common equations we have, you need to get the equation, correct equation to that condition, because we discussed about the 4 cases, right? Source is moving towards the observer, and then we can have source is moving away from the observer, and then source is at rest, but observer is moving toward the source, and source is at rest, but observer is moving away from the source. According to that, you need to use the formula correctly, right? So that's the important part. So now common formula that we discuss is, write that in here, common equation we discuss is frequency that you will hear a later time should be equal to F times velocity of the sound plus or minus velocity of the observer, and you're going to divide that by the velocity of the sound and minus plus velocity of the source, right? So according to that, you need to get the equation from that by thinking what is happening in the question. Okay. So now there is a train has a band playing song on a flat car. As the train approached the station at this speed, a person on the platform hear a trumpet play a note at 350. So sound speed, we're going to take it at given. So now, which case is this one? That's the first thing you need to understand. What is the source is, what is the observer is. So now source in this case, actually train, because train is the where that you play in the sound, right? So train is the source. So now observer will be, because station is the observer, that's where the person is sitting. We can say station is the observer. So now what is happening in here? Train approach the station. That means the condition or the configuration that I have is, I'm going to write part A in here. What is the frequency of the trumpet? That's what you need to find it out. Before that, I'm going to write the case that I'm working with. So case is, source is moving towards observer. Right, so observer is station as we discussed. Source is the train. Right, So now source is moving toward the train. So go back and check that how you get this formula correctly to this configuration. So now since the source is moving towards the observer, you definitely will hear the higher frequency, right? So now you can definitely see that station, the observer station is at rest in here. So that means observer does not have the speed. So that means we observer speed is 0, right? So speed of the train is given. So now you can see as soon as you write that your formula, your numerator will be only left with the speed of the sound. And now what will happen to the denominator? So now denominator, you have the sound and the source both, because both has a speed. But since source is moving towards the observer, you're going to hear higher frequency because it is moving towards you. So when you hear higher frequency, that means my denominator should be lower. The denominator is lower frequency, you're going to hear is higher, right? That value will be greater. Because of that, on the denominator, what will work is negative sign term. Okay, so that because of that, this will be turning into V sound, negative V source. That's the formula that I need to use for this part. Okay. After you know that, you can definitely plug the values. We have all the information. We have V source given as 21.4 meters per second, and speed of the sound asked to use 243 meters per second, 343 meters per second, and then the given frequency is actually F prime, because you see that in here, it's asking what is the frequency of the trumpet. That means it's asking the F. This one is asking F, and this one is F prime. Okay, F prime is given, that is 3520 hertz. Okay, let's plug these numbers and find the F. So now think what you are expecting. You are expecting F to be smaller than F prime because you hear the higher frequency when it reaches to towards you. So now this number I get 3300 hertz. Okay, now let's move into the next part. So now part B is asking to calculate the wavelength. So that is simple. What is the wavelength of the sound? Part B. We know that velocity of the sound is equal frequency times wavelength. Since it is asking the wavelength, that will be speed of the sound divided by the frequency. So we already have those numbers. 3 meters per second divided by 3300 will give you the wavelength in units of meters, right? So I'm going to write it from centimeters after you calculate it, since it is 10 centimeters. Okay, so now let's move into the last part. If the trumpet plays the same note after passing the platform, what frequency would the person on the platform hear? So now in this case, what is happening? So your source, that means the train is moving away from the observer. It's train past you, basically, past the station, right? So now let's write that first. Source is moving away observer, right? when source is moving away from the observer, and you go back and think what will happen to this formula now, right? So now since it is moving away from the station, that means the observer at the station going to hear the lower frequency, right? Because of that, F prime should be definitely less than the F. But your formula, since your source, the observer is still at rest, right? Observer does not move. So observer is at rest, right? Because of that, your numerator is still the sound. But since my F prime should be lower than F, that means my denominator should have the plus sign in here, plus V source. Okay. So now let's plug that in. So now we have frequency when it comes to the station, you had the frequency 3300 earlier, right? That is the frequency 3300, and then you have sound is 8243, and you're going to divide by 243 plus the source 821.4. So that will give you the F prime. So F prime should be lower than the F. So that is given by the calculation in this number. Okay, let's stop the worksheet 12 here.